department, working in routing software for quite a while, essentially in ISIS, fast convergence, and fast reroute implementations. And since now a year, a little bit more than a year, I've been asked to work on a different project called Routing Proximity, which has to do somehow with routing and also with application networking. So the scope of the presentation is to give you in 1 hour an overview of the project, what we are working at, in both Cisco side, so at the implementation side, and at the standardization side, so IETF and IRTF, and see if the question I have is to see if you have, as service providers, the same kind of issues, and if this kind of work can be of any interest for you. So as said, the talk will be in English. My Polish is very rudimentary, so I wouldn't even try. So, as you can imagine, and as you are a network operator, you know it much better than myself, caching, replication, object location is vital. So whatever you have in an application network, you have to distribute it across your network infrastructure. And therefore, accessing all these objects becomes challenging and may raise new issues. Typically, the typical example we always take is when you find a movie somewhere on a server, so the movie is replicated at different locations in the network on different servers, which one to choose, and especially what are first the criteria you're going to use to select one rather than another, and what are the mechanisms that allows you to make a selection. We are talking here, obviously, always from something that starts at the application layer, but at the application layer means many different things. A traditional content distribution network, a peer-to-peer overlay, controlled or uncontrolled. We know that peer-to-peer may have different flavors, so you have the mostly commonly used BitTorrent architecture with trackers, which is a kind of half decentralized way of doing peer-to-peer, and then you have the full decentralized peer-to-peer model like eMule and others, where you don't have any type of server anywhere, so where communication is done directly between peers. So in all those contexts, the issues are quite the same. So you want to be able to understand where are the peers, where are the servers, where are the hosts, where is the content, how to select, how to choose among different locations of the same content. So I don't know if this is the case for you. I would presume, because everywhere I go, I find exactly the same numbers. So it looks that in today internet traffic, up to 75%, and in some cases even more than that, is peer-to-peer traffic. So it means that it's a substantial part of the traffic. The problem is that it's not the traffic that generates most of the revenue. So there is an unbalanced situation between resources utilization and revenue. So that's why many service providers came to us and say, okay, we have a problem. Let's try to address the problem in a more, should I say, technical way without too much of enforcement, because some service providers try to really enforce some rules to their peer-to-peer community, but it didn't work well. So let's try to find other ways to do this. So this is the typical example. At the application layer, you just see this. So you see that you have a client somewhere, whatever client is, in a peer-to-peer overlay or in a traditional CDN network or a browser, whatever. And you see many copies of a movie, for instance, or many instances of a given cache, and you have no idea what's underneath the connectivity to reach those ones. The service provider sees something else. The service provider has the topology, so he knows the autonomous system boundaries, the topology inside an autonomous system. You run your IGP, so you know the shortest path from A to B, and so on. So you know everything. So if you ask the application to select alone the best copy of a movie or the best object, the application will do it, but according to application criteria that could be completely opposite to what the service provider would like to use. Typically, an application will measure a round-trip delay, and if it is half of a millisecond shorter this way, it will always go this way. While a service provider, knowing the topology, the boundaries of the autonomous system, the cost of transit traffic, and so on, we would like to tune a bit the selection. Another example is peer-to-peer overlays. If you take any peer-to-peer network, most of the time the selection on which peer to use to download the given content is based on the uplink capacity of that peer. So if the peer is known in the overlay with a big pipe, it will be preferred wherever it is, even if it is at the other side of the planet. And when you click, you trigger a lot of inter-provider transit traffic, which is the most expensive one. So clearly, even if we take different applications like CDNs or peer-to-peer overlays, caches, whatever, typically it always results in this question. So please tell me the closest IP address, the closest to me among those IP addresses. So I am number 192.168.10.1, and I have a list of other addresses. Please tell me which one is the closest to me. Now, who can answer this question? Well, the only person that can answer is the person who owns the topology, so the service provider. You may have also some external source of information in terms of topology, because you may use a looking glass server, write databases to have a clue on who is where, but you will never have the exact topology that your selection is going to use inside an autonomous system, because this is hidden. So far, since the problem is not new, we already had some attempts to address the issue. And we had different schemes based on network measurements, round-trip delays, latency, and so on. DNS-based, try to understand where are you located and if it is a good choice, and so on. Manual configuration, just static configuration on the boxes. GPS coordinates, and so on. So different schemes have been tried over time, but with conclusions that none of them was really efficient in terms of selection. First, because no one has access to the real topology. So if you select to download a movie from A rather than from B, you have to understand what are the resources you are going to use to download your movie. And nobody can tell you this. So all the schemes that have been developed before had this issue, is that most of the time it's a guess. So sometimes it works, but many other times it doesn't. So now, since a few months, we try to address the problem from the routing side. So I said, okay, the topology is at the routing layer. Let's try to leverage this information and to derive something consistent to give to the application layer. Obviously, it raises all the questions, but it looks a promising way to explore. So the idea is to have a component in the middle between the routing layer and the application layer. Something that it's owned by the routing layer, in the sense that it's operated and owned by the service provider, and delivers what we call proximity services to application entities, whoever needs proximity services. Proximity being the ability of find the best choice for selecting something, whatever this something is. So it's kind of a client-server transactional model, so very simple. It's very close in its operation mode. Is very close to what DNS does. You need to translate an IP into a name or a name into an IP. You send a request to DNS and you get the reply. This is it. So again, if we go to this model with this kind of request, I am IP address number X, I have IP addresses number A, B, C, tell me which one is closer to me, then this request goes to the service provider proximity server. The proximity server runs some special algorithm I'll talk about later, and replies, and so the application entity can make some use out of it. Now, the term of closest obviously refers to a context. A closer could mean routing closed, so from a topology perspective, if it is closer. It could also be from a performance perspective. Tell me what is the best path in terms of delay between those nodes. Closer could be also an administrative, a configurable options, a monetary cost. I prefer to select peers that will generate traffic from this service provider rather than that one, because I have a peering agreement with one, not with the other, and so on. So the term of closer is very variable. So again, we wanted to leverage what available into the service provider space. And the service provider space has a very helpful, very powerful amount of information, which is the routing database, BGP, OSPF, or ASIS, because all your topology is in there. So anything you want to relate to your topology is in those databases. So we leverage this. We define a very simple protocol, request-reply based protocol, very lightweight. We don't want to do something complex just because we want to scale, because we have to scale in the same magnitude of DNS scaling. So you may receive thousands and thousands of requests per second, so you don't want to have much processing on those requests. And we want to adopt the KISS principle. The KISS principle is keep it simple, straightforward. So as simple as you can. Yeah, normally the last S was not really straightforward. But to be politically correct, we say straightforward. So keep it simple. We know that we're not going to address all issues. We always have cases where it may not work optimally. But if already you cover, I would say, 80% of the case with a simple solution, it is good to do it. Okay? Always try to be pragmatical, not to be too scientific, and try to come with a complete solution if it costs too much in complexity in operations and deployment. So why did we choose to work in the routing layer? First, because the information is in there. Second, because the interface to the routing layer, it's already there. We don't need to specify anything new. How can you collect routing information? Well, ISIS adjacencies, OSPF adjacencies, and BGP sessions. You support those three, you can collect any information. So you don't need to specify, to agree on anything new. Then you have the protocols. The protocol have excellent proximity properties. If you think about link state routing, in a link state database, with the link state database, you can compute any path between any node, from one node to many nodes, from many nodes to one node, from one node to another node, any combination, and you can do it with one computation. You don't have to run multiple computations, because this is how link state protocols work. You can leverage BGP with this number of attributes, say as path, communities, local craft, MED, and so on. So you leverage all this. Eventually, you can even leverage route tags in the IGPs. In some specific cases, it's not the major advantage, but still. And so you can base your proximity computation, so try to determine the distance between nodes, between IP addresses, not only on IP addresses, but on any other type of attributes. Very simple idea. If I'm a service provider, I don't know if I have a diagram. Yes, maybe later. So if I'm a service provider, I would like that the application will select peers, servers, cache entries, whatever, that are located in the same POP. Who is going to tell me the POP location? Well, most of the time, service providers deploy customer prefixes into BGP with a community that determine the POP, the city, the region, and so on. So you can leverage this information. Very important, by using the routing layer in order to determine the location of IP addresses, you make consistency between the choice you are going to make for your selection and the choice that the routing layer will make for forwarding the data. Because at some point, when you select a peer rather than another, well, that peer will start transmission of its content, and so it will use a given shortest path across the network. This shortest path is determined with the same information, so link state database, BGP databases, as the information you use to select him. So there is consistency between the two. The information is real-time updated. Routing protocol converges hopefully pretty fast. So if you think about fast convergence now, we can converge the whole network in less than 200 milliseconds. And so it means that the information you will use for your proximity computation will also be updated to the latest topology changes in the network. And obviously, you do not invent anything new in order to locate IP addresses. And so you leverage all the existing and future enhancements that are under work in the IETF and others in terms of protocol extensions, new attributes, and so on. Oops. So just stepping back, and the requirements, where this story starts from. Service provider first service provider had this problem of high resources utilization by peer-to-peer networks. And also application layer had some components like CDN networks, even voice gateways, replication across the networks and so on, that would require and do require mechanism in order to improve selection. If I have the choice between two, which one to select? This is a typical problem at the application layer. Peer-to-peer is the major issue, because here, in addition to having a technical issue because of resources utilization, you also have an operational issue because the service provider operates the network but doesn't operate the peer-to-peer network, so you need cooperation between the two. So the first requirement was we need to improve the scheme at both sides. So we need to deliver something that will make the service provider more happy because he will see the resources utilization going down. But we want also to do something for the peer-to-peer overlay, because if you don't give something, nobody will adopt it. And peer-to-peer overlay may completely ignore these new ideas. So we need to improve also the scheme for peer-to-peer overlays. And this is the most important aspect of the requirements. We have to consider the different scenarios. I talked so far about content download, but there is also content upload. And with content download, typically the client of an application wants to know what is the best choice for me to download. But a content provider may also want to ask the same question, saying, what is the best choice for me to upload? Where should I upload my movie in order to better pre-position it here or there? So taking into consideration different aspects of the different scenarios of application networking. Preserve confidentiality and security. As a service provider, you are going to deliver proximity services, but you don't want to publish your topology. You don't want to give out the details of your BGP configuration or your ISIS topology. So you have to preserve this. Also, the application, the peer-to-peer overlay, don't want to tell you much more about their organization, where are the peers, what kind of data do they share, and so on. So there is preservation of confidentiality at both sides. We should be able, with this new scheme, to work with any application. So today it's peer-to-peer. Today it's peer-to-peer, mostly BitTorrent, mostly with trackers. But we're already seeing the peer-to-peer layer that things are shifting towards a trackerless architecture. Even the new version of BitTorrent doesn't use trackers. eMule doesn't use trackers. So there is a shifting and everything moves on. So today we have an architecture, but probably in 2 to 5 years, this architecture will be gone and replaced by another one that will be replaced 2 years later. So we have to be sure that what we are preparing today has some sort of usefulness also in the near future. And obviously, we want to be interoperable, so we don't want to make this a proprietary solution. We need to make sure that we standardize what needs to be standardized, such that you will be able to have multi-vendors and interoperability in between. So again, taking back the very first slide, in this context, the client, so the red box at the bottom, will send a request to the proximity server owned by the service provider, saying, okay, I'm client, IP address, blah, blah, blah. I have the choice between server 1, 2, 3, 4, giving the IP addresses. Please, Mr. Provider, tell me which one is closer to me. And the service provider, according to the topology, will reply with a ranked list, saying you have to prefer this one, then this one, then this one, and so on. Obviously, the service provider could do its own game and say, always choose the one which is very best for the service provider, then I don't care about you. But you will do it just once, because at the second time, the application will just ignore and not even ask you anything. So cooperation is really something that must be present. Another example is when you have peers, and it happens all the time, in different service providers. A peer-to-peer overlay doesn't take care about AS boundaries. So a service provider may want to prefer you to select a peer which is located in the same autonomous system, or, if it doesn't have this choice, to a friendly autonomous system, in the sense where the cost of the transit traffic is lower than another. And so you can leverage BGP attributes, check the AS path, and see which one to prefer. So this is something, just a repetition. So proximity is based on routing layer. Routing layer is BGP and IGP databases. The confidentiality requirement is granted because proximity is operated by the service provider. So the service provider just replies to request, doesn't deliver the topology, doesn't tell the application layer or the peer-to-peer overlay, this is my topology, this is my BGP database. And at the other side, the application just asks through very simple messages, tell me which IP address is closer to me. So nothing that the service provider doesn't know already. Now, due to the diversity of applications that would use this service, it's not always easy to determine what is the precision of the computation that you need. So in the case, if I go back, to this example, what the provider here would like to do is try to confine the traffic on a given space. Now, if you leverage the routing database, you will have a computation that will give you a lot of details about the shortest path the traffic is going to take, and you can measure the difference between shortest path and come to say, if you select this one, you have one hop less than if you select that one. But maybe we don't need that precision. And this is even more true when you want to address cases for different applications with the same solution. So at some point, you want to come to at the left side, you have the real topology. At the right side, you need the topology that you would need for your proximity computation. Ideally, from application purposes, you would like to identify the POPs. Where are the POPs in the network? Because you would like to confine the traffic as much as possible in the same autonomous system to avoid transit traffic, and if possible, inside a POP to avoid to use your backbone. So this is the topology you would like to have. How to derive from the left information and to derive the right picture? Well, we have a set of algorithms that are not much different from what is used by SIS, OSPF, and BGP. And it allows you to have an aggregated view of the topology, such that the proximity server that runs and receives all the requests pre-compute this topology. So the proximity server take all the link state databases from SIS and OSPF, the BGP database, aggregate all this information, compute a high-level view of the network, and then start receiving requests. And the requests will be simply replied based on which POP and on which autonomous system the addresses are. So it's much more efficient and scale much better. So we have an implementation, and we believe the latest test we've done, I mean, it's in a lab, so we just blasted thousands and thousands of seconds, but a single process can handle, I think it's between 8 and 10,000 requests per second. So it's something that it is very highly scalable, because on a single process, you just run a parallel process and you multiply the capability. And this is also one of the requirements. So the whole proximity is based on preference lists, so a ranking list with an algorithm behind that computes the ranking. Yeah, as I said before, we may want to use the last bullet of the slide. We may want to use other attributes. So far, we address a very simple problem, which is tell me among those IP addresses which is the closest to me. But we may want to play with other attributes than just IP addresses. We may want to say, if I have the choice between Autonomous System 1 and Autonomous System 2, which one I have to choose? So having the capability to answer proximity requests based on IP addresses and BGP communities, autonomous system number, AS path length, AS path content, and so on. So without entering into the details of the algorithm, as I said, routing protocols have very good proximity properties, capabilities. So we just tweaked one more, the SIS and OSPF algorithm, so the shortest path first. There are different variants. It's called forward SPF, reverse SPF, multi-route SPF, also a modified, an algorithm that is taken from the BGP path selection algorithm, and so on. A combination, a big soup. Put it on the oven, 20 minutes, and then it's okay. So the scope of those algorithms is either you compute the proximity on a per request, so you receive a request, you extract the information from the request, you compute, and you reply. But this requires your algorithm to be very, very fast, because if you receive thousands of requests per second, you will have to do thousands of computations per second. So another approach is to say, no, let's try to pre-compute something. So we pre-compute a higher level topology based on the elements that are of interest into the proximity, and then try to cache as much as we can the result of the computation, so any request will not trigger a new computation. Again, confidentiality is preserved. The service provider doesn't deliver routing information. The application layer doesn't deliver application information. So the both layers are okay with this. How to make the proximity service known to the outside, because it's a service that the service provider is going to deliver. Well, there are not really challenges here. You just use whatever mechanism already heavily used for this purpose, a DNS. I mean, a given host name or a service name on the DNS. You just use an anycast address or whatever. It's not really, there are no really issues here. Signaling. So there is a client, there is a server. The client is any application client that wants to have proximity services, and the server is the proximity service that computes. So we need a protocol in between the two. It's a very lightweight protocol, request reply. But even if it is a simple protocol, we need to standardize. So this may take some time, because as soon as you standardize one bit, you will always find 10 people with 10 different understanding of that bit. And so since we are much more than 10, it will take quite a few days or months to standardize. We are in the process of standardization of this protocol. The process just started last ATF. There is a new working group called ALTO. ALTO stands for Application Layer Traffic Optimization. And the goal, I have some slides that give you more details on this. The goal of the working group is to standardize a protocol for proximity services. Well, proximity is more a Cisco terminology. In ALTO, we use an ALTO terminology, but we want to say the same thing. So the protocol will be that will be standardized will be at least will allow to send and receive proximity requests and replies based on routing information. Will contain the minimal set of bits and bytes in the packets just to improve the scalability. So the scenario here is you have the client. Well, in this case, it's a peer-to-peer overlay. So you have, let's say, peer number one, that in the peer-to-peer overlay, so in the eMule or BitTorrent or whatever, found that the given movie he was looking for is available on peer number 2, 3, and 4. And rather than just selecting based on what the peer-to-peer network tells him, the peer-to-peer usually selects based on the uplink capacity. So in this case, you could select peer number 4, which is the peer at the other side of the planet. In this case, peer number 1 will send a request to the service provider, to the proximity server of the service provider, saying, okay, I am IP address number 1. I know IP address number 2, 3, and 4. Which one is the best for me to select? So again, it's a request that is sent to the service provider. The service provider replies, and then it's still the application choice to select the best peer. Now, an application may combine different criteria, not only routing proximity. The idea is, anyway, to take into account routing proximity. So from an application perspective, if you look, I don't know if you can see it on the slide, but the links connecting the peers to the network have a different thickness. So peer number 4 is the one who has the best uplink capacity, which would make the application to select this one. But from a routing proximity perspective, the proximity server here will probably reply to peer 1 that peer 2 is the best choice because it's in the same autonomous system. So then it's the application to choose which one to prefer. Later on, I'll show you a slide that gives you an idea on the benefit of selecting based on routing. Just to demonstrate, and it has been demonstrated, in both a simulated environment and in a real case with a provider in the US, Comcast, that selecting in this way is more efficient for both application and service provider. So same here. The requester, whatever it is a peer on a peer-to-peer network or a client on any application, will send a request, and here the choice, the ranking that the proximity server will compute will be based on many different criteria that could be just strict shortest path. And in this case, I would prefer the peer that is really closer to me in terms of autonomous system hops. But it could also be based on some preferences you have between service providers, on exchange points, on peering agreements, and so on. So there are other criteria that comes into the algorithm. So just as a summary, you have servers, proximity servers, operated by the service provider, collecting routing information, doing and executing some algorithms, and then you have the proximity clients, consumers, that for any application purpose sends requests to the proximity server to get an idea on a ranked list, a preference list of peers, servers, whatever. Very lightweight protocol in between for requesting a proximity or deliver a proximity. We have different implementations options on those servers. Today, we have an implementation, but that uses a dedicated box, I would say. It runs on a server. It's called a service gateway, and it's part of a wider architecture in the next generation of content networking. It's called service routing. It's something quite new, so it's a bit out of the purpose of the presentation, so I just wanted to mention the name. But we are also evaluating the possibility to run the proximity server in a router directly, which will make even easier from a signaling perspective, because a router already has the routing information, because it's a router. So you don't need to collect anything. You have everything inside the router's memory. So it scales better. You have routers everywhere, so you don't need to understand where to place your proximity server. You just activate it where you need them. And so we have some other options. A few words about standardization. So we have today 2 working groups. Well, 1 working group and 1 research group. The working group is in IETF. It's called ALTO, as I said before. And the IRTF research group, IRTF is the Internet Research Task Force, which is kind of the parallel organization of IETF, just for research, so we don't do standardization. And the goal of the P2P RG is to work on research for any type of peer-to-peer issues. So it goes well beyond just the proximity particular problem or particular solution. It includes any peer-to-peer research. Now, the IETF working group ALTO met at last IETF in Minneapolis in November. We had our first meeting, and among the presentation, there was an interesting presentation from Comcast that did some experiments in their network, and they demonstrated that keeping the traffic localized in the autonomous system reduces a lot their transit traffic and improved the performance of the peer-to-peer network. The peer-to-peer network being a BitTorrent tracker-based network. And they were quite positive on the idea, because I don't know if you know it, but Comcast had some severe issues with peer-to-peers, and they are one of the networks that suffer most from peer-to-peer traffic, because I think up to 80% of their traffic is peer-to-peer. And so for them it was a very important issue to address, and they seems to be happy with the approach the IETF is being taken in terms of localization. Now the term localization needs to be redefined, because localization in the terms, keep the traffic local as much as you can. So don't try to go back and forth across the backbone. This is the problem statement draft from Enrico Marocco, who is the co-chair of the IETF working group ALTO. So it's typically oriented on peer-to-peer networks. So the charter of the group is also oriented to address the peer-to-peer traffic and resources utilizations. It clearly explained the problem where you have the peer-to-peer overlay that do not consider the underneath infrastructure. And so selection on peer-to-peer networks is based on criteria that are ignored by the routing layer. And so this inconsistency between the two results in a lot of utilization of backbone infrastructure. So we have here, I explicitly list here the requirements expressed in the IETF requirements draft. And as you can see, it's just a repetition on the same requirements list we had in the Cisco proximity implementation. So we are really in line with this approach. So first, improve the schemes for both service provider and application layer, because if you make things better just for one of the two, the other one would just not using it. Ensure security confidentiality between layers, and this is the case. We just don't share information between the two. You want to be somehow agnostic in terms of application. You don't want to be bound to just one type of architecture in the application layer, because applications are very volatile. The architecture in the application layer evolved much faster than in the routing layer. So if you base a solution on a specific application architecture in 2 years is obsolete. So, and finally, standardize what's need to be standardized and nothing else. So you don't want to standardize the algorithms, because those are an implementation specific. You want to standardize just the protocols. You have in this context two main aspects. You have technical aspects, so the topology, the type of traffic, the congestion, the performance measurements, and so on. But then you have non-technical aspects, like confidentiality of obviously, and probably most important, the interworking, the partnership between layers. You need cooperation between peer-to-peer overlays and service providers. And this one was the first milestone we had in the IETF constitution of the working group. Before having the working group, we had a meeting last year, it was I think in May, at the MIT in Boston, and for the first time we had service provider and peer-to-peer vendors, if we can use the term vendor for a peer-to-peer. And at least they started to talk to each other and start to cooperate. And also now in the IETF, the draft that is published by Comcast and that explains the result of their tests in their network is, I believe, co-authored also by a person from BitTorrent, which is the mostly used peer-to-peer client and architecture. So interworking between the layer is a must. And having this, it allows you to hope to solve the problem. Again, different components requires different solutions. So proximity, it's very wide. It englobes different modes of computation. Service routing versus traditional CDN. So I briefly said service routing what it is. It's the next generation of content and service distribution networking versus tracker-based peer-to-peer network versus trackerless peer-to-peer networks. So you have many different architectures. You are going to have even more different architectures in the future. So what you built should be just kind of a foundation for something that is going to evolve. And keep it simple, straightforward. So Alto the work has already started. Standardize the protocol between, in the IETF terminology, an Alto server and an Alto client. So in Cisco we say proximity server, proximity client. I think one draft has been already published for review. I'm about to submit the second draft probably next week. So we're going to have another one. We are working in the sense that we try to merge. So even if we have different ideas, we don't believe that the ideas are so far one from the other. So at some point at ATF we are going to merge. And especially, again, the Cisco proximity implementation fits pretty well the model that has been described in ATF. So we are pretty confident that we are going into the right direction. The current proposal, not all of them are in the IETF context. I'm especially thinking about the first one, the PANDO proposal. But it's worth to mention it because this was an implementation used by Comcast to test the effectiveness of the Alto mechanism. So they had an implementation that reply to requests from BitTorrent in order to guide the peer selection of BitTorrent, in order to keep the traffic localized in the same autonomous system or in the same region. And this is what they used, and they were pretty happy about the results, which is even better. Then you have Deutsche Telekom Oracle, so Deutsche Telekom Labs, that published a very interesting paper on an architecture and the protocol they developed that is very, very close to what Cisco Proximity is doing. And I took one of their slides, put here in the presentation as the last slides, because it gives exactly the picture before and after. And the University UCL in Belgium proposed an extension of this Alto proximity architecture based on another requirement which doesn't really belong to the application layer, but it does belong to routing itself. And one of the examples they gave is when you have a multi-stack, so multi-address families. So you can reach a given host through V4 and V6, which one to choose. And so you would ask the service provider to tell you the preference based on whatever criteria. And so this is a scheme they documented and even proposed to ATF. I think I'm on time. Yes. So this is the last slide, I think, of the presentation, and it's taken by the DT Labs slides. And it gives you exactly where we are and where we want to go. So at the left side, you have the representation of peer-to-peer overlays on top of service providers. So this is based on a simulated topology, but taken from real BGP databases. So it's a rebuild of the representation of both the most major service providers and the overlays. And at the right side is, if you just apply a very simple rule, select a peer if he is on the same autonomous system. So we are not even talking about select it if it is closer to you in the same POP or in the same network or whatever, just in the same autonomous system, and you have this. So you see that inter-provider traffic substantially decrease, which significantly reduce also the cost of peer-to-peer networks. This is also being demonstrated by Comcast, because as soon as they tried the Pando implementation, I mean, it was not really the Pando implementation, it was the Yale University implementation, but it was kind of organized by Pando. And they came to the same conclusion. So you keep the traffic localized, you saved a lot of transit traffic, and so transit costs. So we'll see more at next ATF. At next ATF, we're going to have two meetings: the Alto meeting for the standardization of the protocol, and the P2P RG meeting for presenting new ideas in terms of proximity, but also peer-to-peer interconnections and so on. I think this is the last slide. Yes, so I finished the presentation. Any question? Okay, thank you.